Participants, let us start the 10th live session on payment materials. In today's presentation, we would be discussing about assignment 9 questions and also the brief summary of week 10 lectures, followed by few numericals on week 10 lectures. When it comes to the week 9 questions, most of the questions are of theoretical, which we can answer directly. For example, if we take the first question, the diameter of standard sample prepared by superpay method is. So when we are about to choose the diameter of the sample that we are going to cast, it depends upon the maximum aggregate size. So we need to make sure that the diameter of the sample should be 4 times of maximum aggregate size, so that when the compression is applied, the edge effects will be eliminated. So the option would be B, 4 times of maximum aggregate size. After initial number of gyration, the mix should have percent air voids of how much. So initially we would be checking these asphalt mixtures for particular number of initial gyrations, so that the required air void should be in the range of 9.5 to 11. Question. Calculate the GSP of final mix if RAP is 30%, if GSP of virgin aggregate is 2.647, GSP of RAP is 2.549 and GSC of RAP is 2.731. So here the question is, we need to calculate the specific gravity of mix. When I say mix here, it is a mixture of reclaimed asphalt pavements RAP and also virgin aggregates. So let us say total we have 100% is the mix. In this 100%, if we remember previously, if we wanted to calculate the GSP of aggregates, so out of total 100%, let us say 50% are coarse aggregates. Then how we used to calculate? 50% by GSP of coarse aggregate plus remaining 50% are fine aggregates, then 50 by GSP of fine aggregates. So for any GSP mix, if the coarse aggregates and fine aggregate fraction is known, and if their respective specific gravities are known, this is the way we used to calculate the total bulk specific gravity. So in the given problem, for the mix, they have given the properties of RAP. So here the RAP has GSB of RAP is 2.549 and also GSC of RAP is given. Directly substitute. It is mentioned that RAP is 30%. So 30% divided by what is the GSB of RAP? Plus, if the RAP aggregate is 30%, out of the total mix, remaining 70% should be virgin aggregates. So 70% divided by, what is the GSP of virgin aggregates? GSP of virgin aggregates. So if you see this, 100 divided by 30 divided by GSP of RAP is 2.549 plus 70 divided by GSP of virgin aggregates is 2.647. So if you do the calculation, we will get the GSP of mix as 2.617. And if we look at the fourth problem, in a project, it is proposed to use 30% of fine wrap. After extraction and recovery, 8% of wrap binder content is obtained. So in the given wrap, the wrap OBC is given as 8%. If the OBC of final mix, so OBC of mix is given as 5.5%. Calculate the percentage of wrap binder in the total mix. So here total binder content in the mix is 5.5. Okay. So in this 5.5, how do we get this 5.5? Usually when we have the wrap aggregate, so this is the aggregate, surrounding the aggregate there must be some binder. So whatever the binder presented around the aggregate, plus we will also add some new virgin binder. So if somebody asks about the total binder content, so this binder around the wrap aggregate plus this newly added binder together is called the total OBC. This total OBC is given as 5.5. So this total is given as 5.5. In this 5.5 percentage of OBC, what is this percentage of wrap binder? That is the question. So how do we calculate that? And also it is given that out of 30% of wrap, 8% is the binder. That means 30% of wrap means aggregates coated with bitumen are together 30% in the total mix. In that 30%, around 8% is the only binder. So 8% of 0.3. So this 8% of 0.3, this is actually the binder content in the wrap. So this binder content in the wrap is how much percentage in the total binder content? Already total binder content is given as 5.5. So if we do this 8 into 0.3 by 5.5, we will get as 44. See the fifth question. Calculate the viscosity of new binder in poise. The given data is 5% is the OBC and 5% is the binder in the wrap. So for the wrap, the OBC is given as 5%. And for the mixture, when I say mixture, it is a combination of wrap plus new binder. So the OBC is 5% again. Target viscosity is 3000 poise. That means nothing but the wrap aggregates. If I mix with the new binder content, and this wrap binder already has a viscosity. This wrap viscosity is 10,000. So I have to, this wrap viscosity is 10,000 means it is very stiff. So for this very stiff wrap binder, I have to add some softer binder so that I wanted to achieve the viscosity of 3000. So they are asking that what is that softest binder I have to add so that I will get the target viscosity of 3000. So let me draw a blending chart that you could have remembered. If we know the blending chart, this is very easy to solve. So this is the blending chart. From that blending chart, we know the relationship between viscosity and the wrap content. So y-axis is log of viscosity and x-axis is wrap percentage or virgin aggregate percentage. So let us say here in the starting if I mention 100% of 100% and 0%. Here if I mention 0% and 100%. This means this 100% corresponding to RAP, virgin aggregate corresponding to 0%. What does this mean is, whenever I say RAP is 100% means, in the total mix 100% I am using the RAP. So at that time what is the amount of virgin aggregate? It will be 0. So in the same x-axis we have to observe that when the RAP is 100%, the virgin aggregate would be 0%. Let us see if I am keep on reducing the RAP percentage from 100 to 90, 80, 70, 60 and if the RAP is 0%, that means I am not going to use any RAP percentage. So whatever the aggregate I am going to use is only the virgin aggregates. So whenever the RAP percentage is 0%, then virgin aggregate percentage is 100%. If we know these two things, then solving this problem would be very easy. So let me write this again. 100%, 0%, 0%, 100%. So first one is corresponding to the RAP. Second one is corresponding to the virgin aggregates. So let us mark the given data. So it is given that RAP binder viscosity is 10,000 poise. That means if there is only RAP, the binder viscosity is around 10,000. Okay. When the RAP is 100%, the viscosity is 10,000. And what is the given again? And also given that 30% is the RAP. So we know RAP is 100 here, 0 here. So 0, 10 might be here, somewhere here it is 30%. Okay. So RAP percentage is 30%. Let us keep that. And RAP binder viscosity we have kept. So they are asking that what is the viscosity of new binder. We know that RAP binder viscosity will be very high and the new binder viscosity will be very low, and that is given as, we have to calculate eta. So if I combine 10,000 and also eta, I will get some other viscosity. That viscosity is nothing but the target viscosity, and that is given as 3,000. Okay. So this is a given problem. We have the RAP binder viscosity of 10,000 and we do not know what is the new binder I have to add. But if I know the viscosity of the new binder, finally I have to get this 3,000 viscosity. So now the unknown factor is only eta. So let us use the similar triangles. Okay. So we know this angle. Let us say this angle. So how do I do this? Log of, what I am going to do is, this is y, this is x. Okay. So log of 10,000 minus log of eta. If I do log of 10,000 minus log of eta, what do I get? This whatever the y I have chosen, divided by, so y2 minus y1 I have done to determine the slope. Now I have to calculate the x2 minus x1. x2 minus x1 is this. Here what is the value? 100. Here what is the value? 0. So this is 100. So just now I have written about this slope. We know that this angle, whatever I have written, can also be written as this log of 10,000 minus log of eta divided by 100. That can be written as same this y2 minus y1 by x2 minus x1. How do I get this y? That is log of 3,000 minus log of eta. Divided by, and this x2 minus x1 would be, so this let us say we do not know. Then 100 minus 100 minus 70. It is just a process of interpolation. So if you do exactly, we will get the value as 1790.73. If you understand that problem, it is exactly similar. Let me draw here the same question.
At one point, this question number 7, not.
Sir? Yeah, question number 7 I will. So if you see the question number 6, they are asking for calculate wrap binder percentage. So exactly same thing. This is log of viscosity and this is percentage of wrap and virgin aggregates. So we know that this. So wrap binder viscosity is given as 14,000. Target viscosity is 4,000. Virgin binder viscosity is 3,000. Okay. So the question is calculate the wrap binder percentage. So we need to calculate what is the percentage of wrap. So let us write this log of 14,000 minus in the previous question is eta. Log of 14,000 minus log of 3,000 divided by 100 equal to this one. This one log of 4,000 minus log of 3,000. Let us imagine this as x. Then how much this will be? 100 minus x. So if we calculate x here, so whatever the x we get is the percentage of aggregate percentage. Because wrap aggregate is 100 here, 0 here. So whatever you got will be, for example, from this side we have to mention. So if I get x, then 100 minus x would be our wrap percentage. Okay. So you will get, they have given the range 18, 19, but you will get in between. So let us come to the 7th question. Calculate the initial residual bitumen content required for the preparation of cold mix asphalt if the percentage of coarse, fine and filler are given. This is also easiest question. So we know directly how to calculate the initial residual bitumen. So this would be 0.05 into coarse aggregate percentage is 60 plus 0.1 into fine aggregate percentage is 30 plus 0.5 into 10. So you will get exactly 7.7 as the value. And if we come to the 8th question, which of the following materials are used for strength modification of cold mix asphalt? As we have discussed in the previous classes, cold mix asphalt can be modified for the strength either by using the cement, fly ash, lime or any of the above. The internal angle of gyration is in degrees. This is a direct question and it is 1.16. So if we come to the summary of week 10, primarily there are 3 topics that have been discussed in this week 10. The first one is performance based mix design and the second is the characterization of bituminous mixtures and the third is regarding the cementitious materials Especially we have discussed about the production of cement and their physical properties and their hydration theory. So why do we even need to go for the performance based mix design? So currently we have Marshall based mix. So why are we not even proceeding with that? Why are we even looking for another kind of mix design? Because the currently existing mix design, which is Marshall mix design, is based upon volumetrics. When I say volumetrics, these are the VMA, VFB and air voids. But if you look at the all these calculations are highly dependent upon the bulk specific gravity of the aggregates. This bulk specific gravity of the aggregates, especially for fine aggregates, we know the variability of the GSP. We could not able to get the repeatability for fine aggregates, especially in the laboratory. As we change the bulk specific gravity of fine aggregates, our volumetrics are going to change predominantly. When we see the change in the volumetrics, we know that our final OBC would be varying. As the OBC is varying, the performance and other responses would be varying. So the current existing mix design is highly variable and it depends upon the bulk specific gravity. In addition to that, recently the existing modified binders and other technologies like Vomix asphalt technology and the recycling mixtures, the mechanism of their response is not possible to just explain by using the volumetrics only. Thereby, we need other parameters which can explain the mechanism of newly existing mixtures, so that we need to modify the existing mix design process. So this performance based mix design is one of such process. This performance based mix design mainly considers about the critical distresses. For example, three critical distresses in the pavement are: one is rutting, another is fatigue, and the third is low temperature cracking. So these are the three critical distresses. If our pavement is reasonably good enough to resist these three failures, then performance better in the field. So before even laying the mixture into the field, we need to make sure that our mixture can have better resistance in terms of these three failures. To make sure that there are four approaches that are in practice and there are multiple approaches, and these four are the main approaches. If we see the brief summary of approach A, let us say currently we have Marshall mix design. So finally we will get the OBC from the Marshall mix design and we will calculate the stability and flow value. Based on those values, we will be determining which mix should be performing better in the field. In addition to that, let us say if my OBC is 5.4% optimum bitumen content, once my OBC is 5.4%, let us say if I wanted to understand how this mixture would perform with respect to the rutting, fatigue and also low temperature cracking. So using this OBC, I will prepare some specimens, cylindrical specimens are according to the specifications required. I will prepare a specimen. I will test those specimens for the test related to rutting, fatigue and the low temperature cracking. If those mixture specimens are able to resist these three cracks in the laboratory, then we can say that whatever the OBC we have decided is the final OBC. If at that OBC, mixtures are not able to meet the rutting, fatigue and low temperature cracking failures, then we need to redesign the optimum bitumen content. Thereby, we can either change the gradation, either we can change the bitumen type, but at the end, we need to make sure that the optimum bitumen content which we are going to use should be able to perform better in terms of rutting, fatigue and low temperature cracking. This method is called approach A. So in this method, strictly we are following the volumetric design, but in addition to that, we are just checking for the performance verification. We are not disturbing any of the existing volumetric requirements. But if you come to the second type, which is approach to volumetric design with performance optimization. So in this process, Let us say I have obtained my OBC as 5.4 like in the previous case, but when I use this 5.4% and when I created or prepared these specimens to test for rutting and fatigue, I understood that they are not able to take the rutting failures. Thereby, what I will do is, let us say I increase my binder percent to 5.5. So then I will again recheck for the performance. When I say performance, it is to resist the rutting, fatigue and low temperature cracking. So here we have the facility to change the binder content just either above the OBC. Initially we will prepare the specimens at OBC and also we will prepare the specimens at higher than the OBC. Still, we will be following the volumetric design process. Once all the volumetrics are satisfied, that is corresponding to the 4% air voids, only that bitumen content will be chosen for the OBC determination. But before finalizing that, we have the facility to change that OBC by either increasing little percentage. Approach A and approach B, there is no much innovation. If you could see, this is almost like an existing process, and these two are the most conservative methods. And if you come to the approach C, performance modified volumetric mix design. So in this process, we are going to modify the existing mixed design process. So usually when we do Marshall, we prepare the specimens, we take some trial binder contents and we determine the binder content corresponding to the 4% air voids. But here we take the trial binder contents, we prepare the specimens, we directly take these specimens to test for rutting, fatigue, these failures. So if they are not able to satisfy or not able to resist these failures, we again change the binder content or change the gradation, and finally we come across some which is nothing but optimum bitumen content. So whenever these binder contents can able to resist the rutting and fatigue and other distresses, that OBC we will finalize. And at that OBC again we will prepare the specimens and we will check for the moisture damage. Whether at this OBC my mix would able to resist the moisture damage or not. If that can able to be resisted, then we need to now confirm, is there any requirement of volumetrics? So let us say VMA minimum. So now we will confirm that this at this OBC whether my mix able to satisfy the volumetric requirement. So in this approach C, we are actually designing the optimum bitumen content based upon the performance distresses. Still, we will check for the volumetrics as a check at the end. But when it comes to the approach D, it is completely a performance design. There is no point of volumetric mix design. So initially we select the aggregate gradation, we select the trial binder contents, we prepare the specimens, we test those specimens for rutting, fatigue, distresses, and once they have satisfied, we again prepare the specimens at the OBC, then we check those specimens for moisture damage, and if that is getting satisfied, we will say that this is the final OBC because we are not going to check for any of the volumetrics. So whatever we have discussed till now, let us say, so in the approach A, volumetrics requirement and additional performance. And this is the most conservative, there is no innovation. And when it comes to, so this is very easy flow chart if you could see. Volumetric mix design, we will determine the OBC. If at that OBC, if the volumetrics are getting satisfied, yes, then conduct the rutting and fatigue at that OBC. If they are satisfying, then come down, conduct the moisture damage. If that is meeting, that's it. Your mix design is finished. This much easy is the approach A. Approach A and B are almost same. But only difference will come is, so we do the volumetric mix design, we got some OBC, but we can actually modify the OBC plus some other bitumen content at two different bitumen contents. The bitumen contents higher than the OBC also we can cast. And in the approach C, this volumetrics can be relaxed and eliminated if performance criteria are satisfied. This is less conservative with medium level of innovation. And the final approach is approach D, in which there is no requirement of volumetrics at all. It is completely depending upon the mixture performance test results, and this is the least conservative with the highest degree of innovation. So these are the 4 types of approaches for balanced mix design or performance based mix design. Using actually the approach here. So when I always talk about the asphalt mixtures, we know that asphalt binder, we assumed it as viscoelastic in nature because we already discussed that the response of this material is time dependent. So it is time dependent and temperature dependent. But truly if we speak, the response of the asphalt mixture is viscoelastoplastic in behavior. What does that mean by viscoelastoplastic? We know that viscoelastic behavior is nothing but its response is depending upon the time. So they have time dependent response. So if we give the sufficient amount of time, they have the ability to recover. So when I say plastic means whatever the amount of time you provide, there will not be any recovery, at least for some percentage of deformation. Let us say 10 mm is the deformation that is being observed on the surface of the asphalt mixture. So if you provide 1 year of time, let us say, you can assume that 7 mm can come back, but still there will be 3 mm of rutting. So this rutting is nothing but the plastic deformation, unrecovered strain. So asphalt mixtures are of viscoelastoplastic materials. They can have a time dependent recovery, and also there is some amount of strain that cannot be recovered. But to understand how much amount is not recovered, this will become a complex analysis. That is the reason why in most of the cases we assume that asphalt mixtures are viscoelastic in nature. This is our assumption. So if we take the asphalt mixtures, their response is affected by, we know, the temperature and stress or strain. So if I keep applying more amount of stress, we know the strain absorbed would be more. In the same way, in the controlled strain experiments, if I apply the more strains, we can observe the more stress. And also time of loading. How do we link with this time of loading? Let us say when I say wheel load is 90 kilometers per hour. That means wheel is moving so quickly. So when the wheel is moving so quickly, the amount of contact on the pavement surface would be very short. So it just come, let us say 9 a.m. the vehicle has come with 90 kmph, it is moving means just 901, within 1 second it will pass this point. So the amount of time the vehicle has stayed on that surface is very less. So if the vehicle stays for very long time, let us say 30 kmph, then the time of loading is more. So the response of the material depends upon the time of loading also. And also type of loading. Let us say if I keep on applying 600 kilopascals of load, constant pressure on the material, the amount of the kind of response would be different. In addition to that, if I apply the loading in a sinusoidal manner, the response would be different. And if I apply the load in a Haversine manner, the response would be different. So the response of the material, in addition to the temperature and stress strain, it also depends upon the time of loading and type of loading. So whenever we test the asphalt mixtures in the laboratory, we need to make sure that because the response is depending upon these 4 factors, our equipments and the test parameters should include these 4 parameters for sure. So to perform this, we have 3 types of test. One is empirical test, fundamental test and simulative test. So out of these 3 type of tests, we have to remember that empirical tests are based upon the past experiences and also some research data, and simulative tests are we would try to represent or simulate the field conditions in the laboratory, but fundamental tests are the tests. So from this test, whatever the data we are obtaining, that data will give the stress strain response of the material. We need the stress strain response of the material so that that stress strain response can be taken as an input for pavement design. So out of these three, these fundamental tests are the one which will give the output required for the design of pavement. So in the current lecture, before we proceed to this simulative test and also the fundamental test, let us observe how the pavement element will behave. Let us say this is our pavement and there is a small element. So that small element is what we have taken here. So there is a wheel load on the top of that small element. So let us say the element is here and the car is here. When the car is here, the effect of, let us say this car is coming with 30 kmph and it is applying a load of 80 kilonewtons load. So if the car is very far from this point A, there is no stress in that element A. The element is very relaxed. As it starts moving towards this, the element tries to take that load, so it has to supposed to deform. So it will not deform directly because that element will have some strength. Here the element is nothing but asphalt mixture that has some strength. So it will try to resist the whatever the load that is coming. To that load it will not directly deform. It will try to resist. How much it will resist, it depends upon the strength of the mixture. So higher the strength, higher the stresses will be developed. If it doesn't have the strength, it will give few stresses and it will automatically deform more. But if the material has more strength, it will try to produce more stresses. So when the car is very far away, the stresses would be 0. So let us say the stresses here are 0. Now our element is here. This red color point is our element. The blue color is, now the car is very far. So you can see the stress is 0. As the vehicle keeps coming, what happens? Stresses will start increasing. So that is what you are seeing. Stresses will start increasing. After some amount of time, vehicle has come and it has been placed over that element. That means there is a lot of load on that element. Thereby, now the element has to use its entire strength to resist that load. So the stresses would be maximum at that point. Then later what happens? If the vehicle starts leaving that point, again the stresses would be reduced. And after particular distance, if the vehicle is very far away from this, then what happens? The stresses would be 0. So this is what the behavior of vertical stress. Vertical stress is nothing but stresses that are developed due to the application of vertical load. So this is a vertical resistance. Okay. In addition to that, so if we have any element, one possibility is there will be a vertical stress due to the wheel load. And in addition to that, there can be some horizontal stresses from the sides. So if I take asphalt mixture is not staying there in isolated place. Surrounding to that asphalt mixture, there will be surrounding asphalt mixture also. What happens? That surrounding asphalt mixture would be compressing this element whatever we are choosing. So that side pressure is what we call as confinement pressure. Initially, when there is no vertical load on that element, that pressure from 4 directions would be there, that is normal. As the vehicle starts to move towards this point, you can observe that this horizontal stresses or confining stresses also would increase. And they would increase to some extent. After some time, when the vehicle starts leaving that point, we can also observe that the horizontal stresses would be reduced. And in the same way, there is a third kind of stress which is nothing but the shear stress. We know whether the material will undergo shear or not. For example, if we take the element and if the vehicle is exactly on the top of the element. So if I have an element and there is a load applying on the top of that element, and if there is a resistance from the bottom also, so let us say 80 kilonewtons I am applying from the top and 80 kilonewtons I have a support from the bottom also, then you will not be able to get any of the shear stresses. Let us say if the load is not at the top or center of the element, the load is applied at some edge, then there is a chance that some amount of material can be sheared. So sheared is nothing but there will be a weak plane that is developed and the material will be moved. So when element, there will not be any shear stress. But let us say, see here, if the material is having the load exactly on the top, there will not be any shear stress. But if the load is or vehicle is just approaching or just leaving, then there is a chance of shear stress. So if you could see the curve, so this is zero shear stress exactly at the element place where the vehicle is above the element. So if you move away from that, you can see there will be a shear stress, and if you also move away from that, there will be a shear stress. So once this, when it is coming towards, it will be of compressive. When it is leaving, it will be of tensile. So these are the three main stresses on pavement element on any kind of pavement at the bottom. So as we were discussing about type of test. So whatever the stress distribution which we have seen, now we try to simulate this situation in the laboratory using the equipment so that we would be able to understand the stress strain behavior of the asphalt mixtures. So if you take the empirical test, we already know the Marshall test. In the Marshall test, you cannot understand any of the stress strain behavior. That is the reason why this is called empirical. Because here all the inputs, the weight of the hammer, the height of the fall, all these details are the test conditions are empirical in nature. And whatever the output we observe here is, one is the stability and other is the value. So we consider the ratio of stability to flow as the criteria. If I have two different kind of mixtures, whichever is having, one will have different ratio of stability to flow and other will have other ratio. This is actually called as Marshall coefficient. So this ratio is used as an indicator of rutting resistance. In addition to that, there is no other information from this empirical test. But if you see the other another test, that is indirect tension test. Here also, so if you could see, so this is the specimen. We will actually mark this specimen with a chalk piece like this, diametrically and vertically. This is to understand that whether the specimen is going to fail in which direction, whether it is deviating from that axis or not, to understand that. And there is a horizontal strip. On this horizontal strip, you can observe that the load will be applied from the top, as you can observe here. So here the thing is, we are applying a compressive stress from the top. This is the compressive stress. So if you are applying compressive from top, from the bottom also there will be resistance. So bottom and top both are getting compressed. Then what happens? This side material tries to expand. So if the material is very strong that it cannot able to fail, then it will still not develop any kind of crack. If the material is very weak, that for the applied compressive stress, if it is very loose and it is not compacted enough, then it will try to show the crack. That is what the failure of the specimen. So let us say initially I have applied P pressure and there is no failure there is no crack. Crack will develop like this. There is no crack. Then I will increase the pressure, let us say another pressure of P2. Then I have observed that there is a crack, so specimen has failed. So the maximum load or pressure at which this has undergone the failure, that is what we have to note down. So this test usually at OBC, let us say if you wanted to understand this indirect tension test, you will prepare the specimens and we will test how much load it is. Let us say it could able to take P1. The same specimens usually we condition for 24 hours. That means we will keep in the water. We are creating the worst condition possible for the specimen. Then the same specimen we will be tested using this equipment, and then let us say it could able to take P2 load. We know that this wet sample can take lesser load than the dry sample. We know P2 will be less than P1. But here the criteria is, let us say P1 is 100, minimum take 85 kgs, that means 0.85%. So it should not be like only 10 kgs it should take. So there is a ratio that is called as tensile strength ratio. To the wet and the dry specimen, the tensile strength it has, that ratio should not be very low. So this is called direct tension test to understand the tensile properties of the material. So this is exactly the way we have discussed previously. Let us say this is the horizontal stress, how it will be increasing, and also the vertical stresses. So the two experiments which we have discussed now, they are empirical experiments. But we have another kind of experiments which are simulative experiments. So predominantly using is, you will understand after knowing this experiment. For example, we have wheel loads on the pavement in the real life. So let us take same kind of wheel loads in the laboratory also. And if we have an asphalt surface, let us say one slab we will prepare. Upon that asphalt surface, we will allow the wheel load to move, let us say 10,000 cycles or 20,000 cycles. So at the end, the output would be, we will give the criteria. After 20,000 cycles, let us say, if the rating is maximum of 10 mm, we have to stop the test. So we will see, let us say, if I have two types of asphalt mixtures. So to develop the 10 mm rating, if this material is very strong, let us say, even with 20,000 cycles also, it was still not failing. But if this material is very weak, within 5,000 cycles also, it will fail. So from this experiment, you can only understand the pass-fail criteria. So the criteria of 10 mm, let us say, the criteria can be anything. Here, for example, I am speaking about 10 mm. So we can only determine whether my given asphalt mixture could able to pass the criteria or fail the criteria. That's it. It will not give any other information regarding, let us say I am applying 700 newtons of wheel load. So what are the stresses generated? What are the strains? What is its response throughout the wheel path? This information cannot be obtained. So this just gives the pass and fail criteria. So in order to perform this simulative test, there are various kinds of pavement analyzer APA. So in all the simulative tests, only the phenomenon or the concept is same. We will be having the wheel load. That wheel load will be moving front and back on the asphalt surface. So the criteria would be the difference in all the cases. Let us say in one of the experiment, let us say asphalt pavement analyzer. Here the criteria is 8,000 cycles. We have to run the wheel load for 8,000 cycles, and we have to prepare the specimens either 4% or 7% air voids. And if the rut depth is, if we wanted to design the pavement for greater than 30 million standard axles, then you should not have the rut depth more than 3 mm. We have to limit the rut depth to 3. If you are going to design your pavement for less than 3 million standard axles, then it is okay to have no rut depth. If your traffic is 10 to 30, we should not have any of the rutting depth more than 4 mm. So if you see here, this is the rut depth and y-axis, these are the number of cycles. What happens? As you increase the number of cycles, initially there will be rut depth of little amount, rut depth keep on accumulates and it will be increasing. So if you have two different types of asphalt mixtures, shows this kind of curve, that means that this one is having more rutting depth, 2 is having less rutting depth, which means 2 is better than the 1. So this relative comparisons and the pass fail, this is also based upon the pass fail criteria we have made. We could not able to analyze any of the stresses and strains. So just like asphalt pavement analyzer, we have another kind of wheel tracker, that is hammer wheel tracker. Using this wheel tracker, we can perform both dry test and also wet test. That means samples can be submerged in the water also while wheel is moving. Otherwise, we can also perform this rutting test only on dry samples also. So here the criteria is, let us say 10,000 cycles or 20 mm rut depth. That means when the wheel starts moving, whenever 10,000 cycles finishes, at that time the experiment will stop. Otherwise, if it reaches 20 mm rut depth even before the 10,000 cycles, that also is the final criteria. We need to prepare the specimens with 7% air voids, and the standard criteria is to allow for 12.5 mm. So this criteria is the only thing that is different in these simulative experiments. Otherwise, all the simulative experiments are of same kind. So as we finish the empirical and also simulative experiments, the other kind of experiment is nothing but the fundamental experiments. So these are the experiments very much required to understand the fundamental properties, the stresses, strains of the asphalt mixture, using which we can actually understand the modulus, stiffness, stresses, strains, their creep behavior. So under the constant load, how their permanent deformation is getting accumulated. So using that, how can I differentiate two kinds of materials? All this information can be understood from the fundamental experiment. These fundamental experiments are of two types. One is static test, another is dynamic test. So when I say static means, let us say if I have a load of 600 kilopascals pressure. So I will apply the 600 kilopascals on the asphalt mixture constantly, let us say 1 hour, 2 hour. So the specimen is subjected to 600 kilopascals for continuously 1 hour, 2 hour. So after 1 hour and 2 hour, we will observe how much is the deformation or how much is the change in thick height. So initially it must be, let us say 150 mm height. As you keep increasing the pressure, the height must be reducing because you are applying a compressive force. So this is called static load. But when it comes to the dynamic load, but usually in the field, it is not a static load, right? Because vehicle will not come and stand there. It will not stay there. Until unless this is a parking space, vehicles on the road, they will be coming and moving. They will not be staying entire day there. So the loading on the field is dynamic. That means vehicle will come to some particular point. After some time, there is no vehicle. Let us say vehicle will come. Then after some time, there won't be any vehicle. Then again some other vehicle will come. After that, there won't be any vehicle. That means in between vehicle to vehicle, there will be a rest period. What happens because of this rest period? Let us say when vehicle 1 comes onto the surface of the pavement will try to deflect. So now the vehicle has been moved away from this. Now this pavement will get some time to relax. So it may try to come to the initial position. If not to the initial position, some amount of deformation can be recovered. So again another vehicle will come, again there will be some other deformation and this vehicle will move, then again there will be recovery. So using these rest periods between the load application is more better simulation of the field loading condition. Currently let us see the static type, which is the static load creep test. So when I say creep test, so with the continuous amount of time we are applying the load on the asphalt mixture, and if we apply that load statically, we are not changing, that is called static load test. This test is also called as flow time test. So we apply some amount of axial load in between some ranges. You don't need to remember them. Code provides all the details. So when is the end criteria? So if I apply 69, let us 69 kilopascals, when should I actually stop the experiment? The code suggests that whenever the tertiary flow is reached or 2% strain. What is the tertiary flow? Let us say there is an increase in the permanent strain, which is nothing but the rut depth. It will increase. High, you can see the slope will be very high. This is having a higher slope. That means a progressive increase in the rut depth. That means there must be a boundary at which specimen has failed. When I say specimen has failed, aggregates have been come out. They are not together. Their compactness has been completely disturbed. That's when even if you apply little load also, all the material will be moving away and you can observe the sudden failure in the material. That point is called actually tertiary flow. So till the tertiary flow, so when you actually start doing this experiment, the experiment will also provide the output along the experiment is going on. Then you can see whether the tertiary stage has been reached or not. Otherwise, you can also until 2% of the strain. So this is the static creep test. So the repeated load creep test, which is dynamic creep test, static creep test, only difference is the load is, you will apply the load, you will give the rest period. Again you will apply a Haber-Sign load, you will give the rest period. Haber-Sign. Haber-Sign means half sine. We know full sine is sine wave is this. So I am applying the half sine. This is actually more better simulation of wheel load. So how? This half sine implies that vehicle is coming to the point, vehicle is leaving the point. After that there is no vehicle, then again vehicle is coming, leaving, no vehicle. So we will apply this sinusoidal load and we will observe the rutting in the asphalt mixture. And at the end, as we have discussed previously, so there is a point where we have determined that tertiary flow begins. So in the static creep test, let us say after 1 hour, you have observed that tertiary stage has come. So that 1 hour will be your flow time. That means material flow time should be always more. If one mixture is failing after 1 hour, another mixture is failing after 2 hours. That means tertiary stage. That implies that second mixture is of greater strength because 2 hours it could able to take the load and after 2 hours only it could able to fail. So flow time should always be more. In the same way, in the dynamic creep test or this dynamic load creep test, the after particular amount of load cycles, the specimen will show the tertiary stage. Those number of cycles should be high enough. That means if a specimen 1 can take 1000 cycles and after 1000 cycles it could reach the tertiary flow. But if the specimen 10,000 cycles. That means till 10,000 cycles the second specimen is able to take the load. So that is called flow number. So if I am going to design the pavement for greater than 30 million standard axles, minimum flow number that is suggested is 740 cycles. That means until 740 loading cycles, that specimen should not undergo tertiary stage. After 740 cycles only, it should undergo tertiary stage. So that we are confirming that if the it is 740 cycles of load, then we can say that it is better in performing the rutting. So those are the actually tests, especially static creep test and dynamic creep tests are to understand the permanent deformation or rutting characteristics of the asphalt mixture. In addition to that, we also have other experiments like resilient modulus test. So this resilient modulus, as we have already discussed in the previous classes, if you see, how do we calculate the resilient modulus? Let us say there is a load applied on the asphalt pavement. Then what happens? If you remove the load, so here you have started the load here, deformation started increasing. When you remove the load, what happens? So there will be some amount of recovery, but recovery might not be until the initial stage. So again, if you keep applying the load, again it will recover, again it will, but you can see that there will be an increase in the strain. So your strain would be increasing like that. And also you can observe that there is a permanent strain. Permanent strain is nothing but what happens with increasing the loading cycles, material will deflect. After million number of loading cycles, let us say, there is nothing to deflect because the entire material has already been compacted and this is very strong, so it will not be deflected. So this permanent strain will become constant. What are the strain remain will be resilient strain. So if we want to calculate the resident modulus, which is exactly like elastic modulus, the deviatic stress that is applied on the material to the strain. So in this experiment, we subject the asphalt mixture either to the confining or indirect repeated load test. Then we will determine the horizontal deformation, and we apply the load of 0.1 seconds and 0.9 seconds loading, and the horizontal deformation will be keep on changing. Based on that, we can calculate the strains. If we know the strain and we already know the stress, we can calculate the modulus value. In addition to that, the extra modulus that we will be calculating is the dynamic modulus. Complex modulus, because if we consider the resident modulus, we are one of the assumption is that whatever the elastic strain that we are assuming at the end of the particular number of loading cycles, it could only capture the elastic behavior of the material. Let us say if you wanted to understand both elastic plus viscous behavior of the material, then we need to use this dynamic modulus. Either sinusoidal or Habermas load we will be applying, but in this dynamic modulus we will not be considering any of the rest periods, and this can be used to define the stress strain relationship of the asphalt mixtures as a viscoelastic material. As I told, this is a complex modulus. The real part would be explaining the elastic stiffness, and the imaginary part would be explaining the internal damping, which is nothing but the viscous behavior of the material. And also the stiffness modulus. Let us say dynamic resident modulus gives the modulus value of the asphalt mixtures. So if I wanted to understand the dynamic stiff modulus using the beam test, we can also calculate the dynamic stiff modulus. But using this experiment and calculating the dynamic stiff modulus is always very complex and time taking. That is the reason why, if we remember in the starting binder class also, we have discussed about few nomographs, shell nomographs, and some Whitsack equations. So using these equations, if we know the stiffness of the binders using the nomographs, we can calculate the stiffness of the mixtures, and also using the MEPDG empirical equation also we can calculate the dynamic stiffness modulus. Another point is, let us say if we have a pavement of thickness, higher thickness, and if we have a pavement of lesser thickness. So when we have two different kind of pavements, what kind of test I need to perform? Let us say when there is a thicker pavement and if I have applied the load on that. So whether this thicker pavement will deform or not, it depends upon the stiffness of this layer. If this asphalt layer has higher stiffness, it could able to resist more this whatever the applied load is. But if you apply the same load above this thinner pavement, what happens? First thing is it will deform. But now I am going to place a very strong concrete base below that. Then there is a lesser chance it will be. So the response of the thinner pavements always depends upon the supporting layers on which it is placed. Whereas for thicker pavements, it solely depends upon the stiffness of that particular asphalt layer. That is the reason why whenever we perform the test on thicker pavements, we choose controlled stress. That means stress can be controlled, but when we choose the thinner pavements, strain should be controlled. So the criteria is when the thickness thicker pavements and the less than 2, we use the controlled strain. This is about the performance characterization of asphalt mixtures. So if we talk about the cement, we know this is a main raw product in the concrete pavements. So how do we actually prepare the cement? So the production of cement usually requires few raw materials. We know cement is very strong because it has calcium and silicate compounds. So to get the calcium and silicate compounds, the calcareous materials, whichever is having calcium oxide like lime or chalk, these are having the calcium, and argillaceous materials which are having silicon oxide and aluminum oxide such as clay or shale. So using these two main raw materials, we can actually produce the cement. So how do we produce the cement? Fine material. So initially there must be some bigger stones of calcium stones or silicon stones. Those stones should be crushed, grinded. They should be made into smaller pieces. So once after making them into smaller pieces, we need to blend them into the correct proportion. It is not that I will be using 80% of the calcium but 10% of silicon. So what is the optimum percentage of blending so that I will get the better strength of cement. So initially we will crush and grind, then we will blend them with correct proportions. Then once after blending them, we need to burn those materials in the environment called kiln, where the temperature would be around 1300 to 1500 degrees. So whatever that material we are keeping in the kiln, the end product would be called as clinker. So this clinker is a final product which we will be using to produce the cement. This cannot be directly used. This can be added with the gypsum. The purpose of adding gypsum would be explained in the upcoming slides. If I don't add the gypsum, what is the corresponding sequences we would be facing when I use the cement addition with the water. So the amount of gypsum that is suggested would be around 3 to 5%. Whenever I keep my materials inside the kiln, it should be temperature of around 1300 to 1500 degrees. So if you see in detail about the stages, the grinding and mixing of raw material stage, where in the drying stage, usually we are not going to add any of the water to the raw materials of the cement. So we directly take the calcareous materials and also siliceous materials and we will be directly grinding them. But when it comes to the wet process, we would be adding around 35 to 50% of water. So whenever I add some water, what happens? It will provide some slurry kind of material. So we need to again use the extra fuel to evaporate that slurry, and whatever the outcome product that is coming would be of powdered. So it consumes some amount of fuel. So this slurry is what we will take into the tanks and we will be mixing them for better homogeneity. So there is another kind of process which is called a semi-dry process, where we will not be adding higher amount of water. We will be adding around 10 to 14% of water, which is not a very common method in practice. So whatever I have mixed or grinded now, whether it is dry or wet, I will be keeping them into a kiln, which is a rotary kiln. So that kiln would be rotating and this is inclined in direction. So this kiln will be having a temperature of higher, which we have discussed previously, around 1400 to 1500 degrees. So when we keep these materials inside this, there are stages of transformation which I will be explaining in the upcoming slides. Say, this is the kiln. Let us see here. So these are the raw materials I am going to keep inside the kiln. So what happens? When the temperature is around 450 degrees, that phase is actually called as dehydration zone. So slowly whatever the water in the slurry form will try to evaporate or dehydrate. When I keep increasing the temperature to, let us say, 1200, that zone is called as calcination zone. So whatever the clay or limestone, those materials will be decomposed. So calcination zone means the compounds in relation with the calcium related, they will be decomposed. If I keep increasing the temperature from 1200 to 1500, then what happens? There will be a compounds. So now after 1200 degrees, whatever the amount is there, when you keep increasing the temperature, you can see there are some dicalcium silicate, tricalcium silicate, some kind of products would be formed, because the whatever the calcium or silicate that is existed, that would be reacting and forming this C3S and C2S. So at the end, now it is completely dry. we will be collecting them as clinker. So that clinker with addition of gypsum we will be using in the construction. What is the chemistry of this cement? So we know that raw materials have a lot of lime, silica, aluminium, iron oxide. So whenever this cement is mixed with water, there must be some kind of chemical reaction going on, and that chemical reaction will lead to the improvement in the strength. That is the reason why every time we mix cement with water, so after few days or months we will see that it will become stiffer. So how it is becoming stiffer? There must be some chemical process going on. Let us see what is that. So when we keep these calcareous and siliceous metals inside the kiln at higher temperatures, there is a formation of few materials. Those compounds are called as Box compounds. The first compound is tricalcium silicate, which is nothing but the C3S. In addition to the tricalcium silicate, we can also observe dicalcium silicate, tricalcium aluminate, and tetracalcium aluminoferrite. So the amount of C3S, C2S, C3A and C4AF, the amount of these box compounds will actually decide the strength of the cement. So what is the purpose of C3S or what is the role of C3S or C2S? Let us see once. So if we see the C3S, out of total cement, around 30 to 50% would be tricalcium silicates, followed by 20 to 45% of dicalcium silicates and 8 to 12 of C3A and 6 to 10 of C4AF. So the main use of C3S is, so this C3S and C2S are present from the kiln stage. So whenever I add water to the C3S and C2S, these three calcium silicate, dicalcium and tricalcium silicates, they react with water, and at the end they will produce a gel which is called as calcium silicate hydrate gel, CSH gel. This gel is extremely important to obtain the required strength of the cement. So if we don't have enough of dicalcium and tricalcium silicates, so water would be more, you will not be able to react with the enough of the C3S, C2S, able to get the CSH, thereby the cement would not be higher in strength. In addition to the formation of CSH, when the C3S, C2S reacted with water, they also form CaOH twice, which is nothing but calcium hydroxide. So we know that CSH is beneficial, but if we have more of calcium hydroxide, what happens? This calcium hydroxide can be dissolved into the water. Let us say now currently the cement, when I added with water, it has formed CSH gel and also CaOH twice. So what happened? CSH is giving higher strength to my cement, but whenever this cement comes in contact with water in future, whatever the calcium hydroxides that are present in the cement, they will be dissolved. Then what happens? The place where calcium hydroxide is present, that will become a porous or void will be formed. So the concrete, which is very solid and compacted in the initial stages, when it comes in contact with the water, due to the excessive amount of calcium hydroxide, it will become porous concrete. Thereby strength would be reduced. That is the reason why the amount of calcium hydroxide production or byproduct should be limited. So C3S reacts very readily. So when we add water, C3S reacts immediately. So whenever it reacts, whenever some reaction, chemical reaction happens, there will be a release of heat. That is the reason why when you hold the cement in the hand and add the water, you feel the heat. So this is responsible for early strength. So C3S, because it is reacting very quickly, it will give the highest strength immediately. So if we want to achieve the early strength, that early strength in the cement is especially because of tricalcium silicates, which is nothing but the C3S. But unlike C3S, C2S, C3S, C2S would be reacting very slowly. So even though it reacts very slowly, it will also produce silicate hydrate gel and also CaOH twice. So after reacting it very slowly, it will give strength. So after 10 days of strength or 20 days, So this strength can be obtained because of the amount of C2S. And also the C3S, which is nothing but the tricalcium silicates, they produces very less quantity of CSH and more quantity of CaOH. As I have discussed already, if we have more quantity of calcium hydroxide in the cement, because this calcium hydroxide is can be dissolved in the water, in future wherever you use this cement, this calcium hydroxide will be dissolved in water and it will make the concrete porous. So our main aim is we need CSH gel, but we need lesser CaOH twice. So CaOH twice, which dissolves makes a concrete porous. So we need to limit the amount of CaOH twice. Hydroxide is, it also makes the concrete porous, but in addition to that, this calcium hydroxide reacts with the sulfide, and this sulfate will deteriorate the concrete surface. So when it deteriorates the concrete surface, that is called sulfate attack. So that is the reason why we need to limit the sulfates. How it is actually going to affect? When CaOH twice is there and when it reacts with the sulfur, it will form calcium sulfates, and this calcium sulfate will react with the C3A, tricalcium aluminate, and this forms the calcium sulfate aluminate. This is the main reason for the deterioration in the concrete. So, in the initially I was discussing about the addition of gypsum. So, if I don't add gypsum, what happens is, in the absence of the gypsum, whatever the tricalcium aluminates that are present, they can lead to the flash set. That means now I have mixed cement with water. So what happened now, it is in good consistency, we can work. Like I can actually pour this concrete into any place wherever I want. Let us say in 2 minutes itself the cement gets very stiff. That means it is having a flash setting. In order to avoid that flash setting, we need to add the gypsum. If you could see the graph here, so as I told, this is a C3S graph. So initially, let us say at the 7 days, there is a compressive strength of 30 megapascals. As the time increases, you can see that tricalcium silicate helping in forming the CSH gels. As it is forming the CSH gels, then the strength is reaching to around 70 megapascals. So you also can observe that the maximum of around 60 megapascals is attained within the 90 days. That means in the early days. But if you look at the C2S, which is calcium silicates, in the 90 days, the strength is only around 35 megapascals. At the end, let us say after 360 days, it also has reached to 70 megapascals. That means the C2S is contributing to the contributing. So till now we are discussing that whenever we add the water to the cement, hydration would happen, CSH gel will form, that is responsible for the strength of the cement. But how much water I should add? We do not know. So that is also an optimum process. So initially when I add some water to the cement, so there should be some paste, and this paste should be in a form so that I can able to pour this paste into any place wherever I want, at least until the finishing of the construction. It should not get hardened very quickly. So there should be some buffer time available for us so that we can work with that cement in the concrete. So that time available is called as the initial setting time. So I have added water to the cement, but slowly from this plastic state it will become hard. So there must be, let us say, some 30 minutes of time. That means within this 30 minutes you have to use this concrete and do whatever the construction you wanted to. Let us say if the time is only 5 minutes available, within 5 minutes it will become hard. That means it is very difficult for us to use. So that time is called as initial setting time. And let us say in 5 minutes it has started becoming hard, but it was not like very hard like a stone. So Whenever it is very hard like a stone, then we can start allowing the vehicles onto that road. It should not be like it will take 2 months to become very hard. So that 2 months that way is not allowable for the traffic. So that is actually not recommended. So let us say if I have laid the concrete pavement, it can able to get the higher strength, then we can allow the traffic. So this final time is called as the final setting time. So the initial setting time is the time when I have added water to the time when it starts losing its plasticity, and final setting time is the time when I have added water to the time when it is becoming very hard. When I say very hard means if I apply some pressure onto that concrete, it should be able to resist that. So these two are the initial and final setting time. If in the laboratory I wanted to determine that whether my cement has sufficient amount of initial setting time or not, so to understand that we have to do some experiment. So as I already discussed, we need to add some water to the cement. How much water I should add so that I have better consistency? That water content is called as consistency water content limit. So how do we do that? We will randomly, let us say, take some cement content and start doing some trial water content. Then I have prepared the cement paste. Now I have the cement paste. So I will fill that cement paste into a mold which is having a standard dimensions. Then I have a plunger from the top. So it is kind of cylindrical plunger, and I try to penetrate that. That means if this is very hard, that plunger will not move. It is kind of penetration test in the bitumen. So if it is very hard, it can't move. But we want that to penetrate at least 33 to 35 mm. So that cement is not very hard. So we will note down the amount at water content actually this penetration can be observed. That water content actually we maintain as the normal consistency limit. So whenever in future if we are going to do initial setting time or final setting time or soundness test, we take the water content as a percentage of this normal consistency. So let us say I got P as the normal consistency. That means P is some, let us say 5% of water of total cement. So if I wanted to do initial setting time, if I wanted to determine the initial setting time, you take 85% of this P and then prepare the sample, and then for initial setting time and final setting time also exactly we have different kind of apparatus where we prepare the specimen of cement. We will try to apply the penetration from the plunger. So in the initial setting time we want the plunger to be penetrated, but in the final setting time we do not want it to be penetrated because we want the cement to be very hard and stiff. So we do not want any marks on the surface. So the amount of water chosen would be 85% of normal consistency. So these are the initial and final setting times. But if I wanted to understand the expansion of the cement, as we discussed in the initial, when the C3S tricalcium silicate and C2S dicalcium silicate, when they react with water, they will be forming CSH gels and also calcium hydroxide. And we have also discussed that if the calcium hydroxide is very high, it can lead to the dissolvement in the water and form the porous pavements, and also can form the sulfate attacks. So we need to limit the amount of calcium hydroxide or lime. So how do I know whether my cement has higher amount of lime or not? So lime has a property of expansion. When it reacts with water, it will expand. So let us create some specimen and try to use the apparatus which is called as Lee-Chatelet apparatus. So this is mainly to understand the expansion behavior of the cement. So here the amount of water that needs to be added to the cement would be 0.78% of P. P is nothing but the normal consistency limit. So we make a cylindrical kind of cement paste by adding to the cement we add 0.78 times of normal consistency water. We prepared the consistent cement paste. So that cement paste we will, let me show the apparatus. Okay. So this is the apparatus. So inside this I will actually keep my cement paste. So you can see These are the two ends of this apparatus. This is AA. So initially there will be some gap. Now what I would be doing is, I will be placing this specimen in the water for hours. So what will happen if I keep in 24 hours? It will try to absorb the water, whatever is possible. After 24 hours, I will again boil for 3 hours at the boiling point. So that means I am going to exaggerate the chemical reaction. So at that time what happens, if there is a more amount of calcium hydroxide or lime that is present in the cement, then it will try to expand. Then we can see that there would be a gap in between these two bars. This apparatus, Lee Chartley apparatus. So if the gap is more than 10 mm, so previously let us say the gap is 5 mm. After 24 hours and boiling for 3 hours, if that is 25 mm, that means there is a gap 20 mm is increased. That means there is a higher amount of lime is present. We do not allow the expansion more than 10 mm. So that is to limit the lime amount in the cement. So in addition to this soundness test, we also have to perform the compressive strength test. So all these tests are for cement. We are not discussing anything about the concrete at the moment. So to perform the compressive strength on the cement, first we need to prepare the mortar. Mortar is nothing but the combination of cement and water. So and also some fine materials to give the strength. So 1 part of cement is to 3 parts of sand is to, what is the amount of water to be added? P by 4 plus 3, where P is nothing but initially we have calculated the normal consistency of the cement. So by adding this we will get some kind of mortar. So that mortar we will be transferring into the molds. So these are the molds. We will transfer them into that. Then upon that we will place the wet gunny bags, and for 24 hours these gunny bags are to maintain the moisture condition. We do not want the water whatever we have added to be evaporated. Mostly it is suggested that you cast the specimens at the evening time, so that the night the temperature would be around 25 to 27 degrees. We can avoid the evaporation of the water. So after 24 hours we will be demolding. So we will be taking out the specimens. Then we have the equipments that are to test the compressive strength of the cement. So that is so. So the cement would be failed at particular amount of load. So that load divided by the surface area would give the compressive strength. And another last parameter for cement is fineness test of cement. Why do we need to understand the fineness test? Let us say when I say cement, this is not a single size. Exact like when I say aggregate, this is a combination of different gradations. Even the cement is of very fine material, it still can have different sizes. So if there are very fine materials, that implies there is a higher surface area on the particles. When there is higher surface area, what happens? Whenever I add the water, there is a higher chance that the reaction would be faster. When the reaction is faster, the heat generation would be faster, the formation of CSH gels would be faster. When the formation of CSH gels are faster, the strength of the cement would be developed earlier. That means it can be, let us say if I have two kinds of cements, one cement with higher fine content, we can observe the higher development of strength at the earlier stages. So in order to understand that, what is the fineness of the cement, that we need to understand. So this can be understood from two kinds of tests. One is sieving through 90 microns. So take the 90 micron sieve. If most of the material is passing through 90 micron, that means most of the material is very fine. Most of the material is very fine means they are very fine in nature, so they will have more surface area. So here the recommendation is whatever that is retained on 90 mm, 90 micron sieve should not be more than 10. That means 90% should be passing the 90 micron. That is one of the direct way of measuring the surface area. And the second way should be plain air permeability. So this is the plain air permeability apparatus. So if you could see here the apparatus. So here this is a plunger. So inside this usually we will keep our fine material and filter paper and also the porous disc. So what we would be, and here if you see, this is a manometer, this is the atmospheric pressure, and here there will be 2 marks. So what happens is, let us say if the oil whatever is present in this manometer, to move from one distance to another distance, it will take some time. So that depending upon the amount of time it takes to move from one place to another place, we can actually determine the fineness. How do we? Let us say the time I have calculated is 20 seconds. So the surface area equal to K into root T. So this T is nothing but the time required to move a particular distance. So K is the calibration constant for the particular equipment. So let us say K into square root of, let us say T1 is 64 for one kind of fine, T2 is 81 for another kind. So surface area would be, let us say K is 10. 10 into root 64, and also another would be 10 into 81. So whatever the amount, if the fines are more, then what happens? It will take more amount of time to move from one place to another. Therefore, the surface area is more. So based upon this, we can actually determine that. So let us see few numericals. Which mixed design approach includes but has an option to relax some of the volumetric requirements. So if you could see here, there are 4 approaches for the balanced mixed design. The approach A is what? We do Marshall mixed design. After that, using the same OBC, we will be preparing the specimens and then we will cutting and patting. If that is satisfying, that's it. Whatever the OBC we have determined using the Marshall stability, satisfying the volumetrics, that would be our final OBC. That is the approach A, which is very direct and conservative. And here we cannot actually modify or relax any of the volumetrics. So in the question they are asking that an option to relax some of the volumetric requirements. No, we cannot actually relax any of the volumetrics in the approach A. When it comes to the approach B, in the approach B also, only difference is that we can actually increase some amount of treatment content, but we still need to satisfy the volumetric design. So it is not the option B also. And if you come to the option D, the performance design, there is no criteria of volumetric itself. It is only completely depending upon performance distress criteria based upon the rutting and fatigue distresses. So if you see the approach C, in the approach C, there is a possibility to relax or eliminate the volumetric requirements if they could able to satisfy the performance related requirements. So option C is the correct option. Field rut test. What should be the air void for preparing the asphalt mixtures? As we have discussed, it is always better to prepare the specimens at 7% air voids, because when we lay the pavement in the initial stages, it will be at in the range of 6 to 8%. So we can observe the initial compaction, and after particular number of years, it will be reaching to 4% air voids. So to observe 3 stages of the rutting behavior in the asphalt mixtures, it is always suggested to prepare the specimens at 6 to 8%, specifically 7% air voids. What is the assumption in WESI's program for quantification of rutting? If you could remember in the lectures, so rutting, whatever we have discussed on the top surface, is not just the deformation of the top surface. This is a combination of deformation of the bottom surfaces also. But currently we couldn't able to calculate what is the contribution of granular layer, what is the contribution of asphalt mixture layer. So if I want to understand this total rutting at the surface of the asphalt, combination of H1, H2, H3, whatever the deformation in the bottom layers. So how do we determine this? As currently we do not have a exclusive experimental information, So we have already existing programs or empirical equations to calculate that. Vese's program is one such process. In that process, the main assumption is the permanent deformation or the rutting or the permanent strain is proportional to the resilient strain. Most of the times it may or may not be, but this is the one of the assumption they have considered. Direct question. The relationship between permanent strain and the number of load repetition completely based upon the past research and also laboratory data, and they have observed that the permanent strain and also the load repetitions are following the power model. Which of the following statement is true? Loading and dynamic modulus without a rest period. We have already discussed that in the resilient modulus, we apply the load, we give a rest period, we apply the load, we give a rest period. But in the dynamic modulus, we apply a Haber-Sein load without rest period. So, A and B. So, loading in dynamic modulus is without a rest period, correct. Loading in resilient modulus is with a rest period. For viscoelastic analysis, which type of test loading is suitable for the assessment of dynamic modulus? So, if we wanted to understand both viscous and elastic response, it is always better to go for tension and compression mode. In beam fatigue experiment, control test should be done for. This also we have discussed. If we have thicker pavements, what happens if we have thicker pavements? If I apply some load, let us say 80 kilonewtons, whether this part will deform or not, it depends upon the properties of this layer, stiffness of this layer. So here actually you can apply some particular amount of stress and you can keep observing the strain in the material so that it implies more strain, you can say strength is less. If there is very less strain, you can say that strength is not very reasonable. So the stress is controlled here, strain is actually observed. So for thicker pavements, we always go for controlled stress. If we have a thinner pavements, that means very thin. Here what happens? You cannot observe the strain behavior here. Why? The moment you apply the load, because they are very thin, exact like a paper. What happens if I apply the load on the paper? It will immediately bend. But here the stiffness of these thinner layers, if you wanted to understand, it mainly depends upon the bottom layers. If I have a strong CTB at the bottom, then the response of this thinner layer would be different. If I have, let us say, soil, then this response would be different. So, in those cases, we will apply some strain, let us say 2% of strain. To produce the 2% of strain, how much is the strength available at the bottom? That we can assess. So, this type is called as strain control. That means strain we are fixing, but we are observing the stresses. But in the thicker pavements, stress we will be fixing and we will be observing the strain. So, in the current problem, the question is, in the beam fatigue experiment, controlled stress should be done for thicker pavements. Gypsum is added during the production of cement. Yes, this is to prevent the flash set. If I don't add the gypsum, what happens? The compounds in the cement, whichever is C3A, they will react very quickly and hard the bitumen. So you wanted to delay that flash set, so we will be adding the gypsum. Which ingredient of the cement is responsible for later strength? So we have 4 ingredients: C3S, C2S, C3A and C4AF. So for early strength, C3S is responsible. For later strength, C2S is responsible. Questions? And are there any other doubts? You can ask. Otherwise, we can close the meet. Okay then, we'll close the meet. Thank you.